Hey guys, what's up? Eddie Alho here with KissAnalog.com. Alright, today we have this little board. It's an op-amp board. And you know what's neat? It's like a test bed, okay? We can use it just to test out op-amps. It's meant to be a preamplifier, but what I like is that it is socketed. So we can take out the NE5532 that comes on it and try different op-amps in there and listen to them. Test them out. So I want to run some tests. In this video, we're just going to do a quick video. I'll show you the schematic of this. I have to reverse engineer, look the parts on there, kind of show you the schematic of this. But then we're going to use this Omicron device. This thing is one cool piece of equipment. It's not inexpensive, but man, it is amazing. It does a lot of things. One of the simple things it does is Bode diagrams. So it can give us a Bode plot of this, puts out a nice signal. We're going to look at the Bode plot on this, okay? And we'll use the Omicron to do that. So, all right, guys, let's see how it comes. And by the way, this is only like $4.99 on Amazon. So, yeah, check out the link down below. I get a whole 1% of $4.99. So, that's pretty cool. Hey, it all adds up, right? So let's check it out. Let's come over here and test.
All right, guys. So what we have is this little board that's really nice. You see the green lights on. Maybe you see the lights on. And I have a Burr Brown chip in there. Okay. It's the OPA 2604. So the input's here, output's here, and power's here. Okay. So it's just a positive power rail. You don't have to do plus minus. It does have left right channel. Although in this case, I'll probably be just using it as a single channel. Okay, now let me show you the waveforms. So there we are. Now, green waveform is the input, 318 millivolts. Yellow is the output, 1.8 volts. So that's gain of 6. Okay, so we have a gain of 6. Here, let's look at the dB gain with the multimeter. Oh, here, let me show you the setup. So the input wire comes over here, and it's being taken off the pot. So it's the middle wiper, and I'm using the outside one for ground. Okay, the signal coming in is outside for ground and the outside for signal. So with the potentiometer, we can decide how much of the wiper, the middle one, we want, right? So here's my DC power coming in up into this cable. And by the way, I'm using a little WattTech, awesome little power supply. I dialed it down to 9.8 just to see how low I could go and still get a good signal. So that 9.8 still gave me a great signal, but I'm going to be putting in a higher voltage than that. No problems there. So putting in the signal, I'm just dialing it down so that I only get 318 millivolts out, and then the gain of this guy gives me about 1.8 volts out. Okay, so now I'm using an automatic distortion analyzer up here, this Kronheit, and 0.008. Now, when I just put the input to the output, it actually did go down to 0, but 0.00 is pretty darn good. 0.0 anything is pretty darn good, I think. But yeah, that's automatic distortion analyzer. Puts out a 1 kilohertz signal on this side, and then it reads the input over here. So pretty nice little meter. I've had this for years and years. Okay, guys, we're here with the nice KPS, what I call a high-end multimeter, a high count, a high bandwidth. It's 9.89 dB. But now look, now I'm measuring the input here. Now, if you notice over to the left, there's a minus sign. So it's minus 989. So let's just say minus 9.9, okay? And it's 320 millivolts, right? All right, now I'm at the output, and it's a positive 5.25. So say 5.3. So we were 9.9 minus, and now we're at plus 5. So what is that? That's like 15.1 dB or something. So it's around 15 dB, we'd say.
Okay, guys,
I did a schematic on this, and I did a microcap just because I already had a partial circuit in here that I just was able to build. So I put the reference designators, R7, R8, so on. I think I've got the correct ones to match up with the board. So this is the input supply voltage right here, okay? And we're going to say we're putting 15 volts in. Now this diode off to the left, D2, he is a protection diode, reverse voltage. So if you put reverse voltage on that pin, he would protect. He might burn up, depending on how much voltage and, you know, the source, current, all that kind of stuff. Might not last long, but you'd know it. But okay, so then there's two large caps at the input. One of them goes right across the input. The other one goes to this voltage divider. This voltage divider creates this bias voltage. You see when I highlight this over to the right, you get this bias voltage. See when I click on, or when I hover over that, it lights up this one. So it sets up a voltage here. So we get 7.5 volts here. Basically what we're doing is we're putting a DC shift on this pin, because since we're only putting in a positive voltage, just one voltage, okay, and the other pin's tied to ground, we're not using a plus and minus voltage rail. We need to float this guy halfway up the voltage rail, and then this sine wave can go through this capacitor. It'll be AC coupled at that point, so it'll be an AC waveform here, and it can go up and down. It can go down to ground, and it can go up to 7.5 volts. Okay, so the input can swing up and down that way, and then over here, the output, when it goes through here, it goes through this feedback, and over on this pin wants to match this one, right? So this guy, so the output basically, to do that, to place a voltage, whatever voltage is here gets divided by this resistor and this resistor, the feedback resistor and the input resistor, and the inverting input. So that voltage gets divided down. So this voltage gets to swing as high as it can. It can go plus to 15 and all the way down to ground. So over here we go about half the voltage, and on this side we can go the full voltage, okay? So that's how that works. And this is also capacitively coupled, because this point here, same as this is DC biased. It's biased at this voltage right here. So, and the 47K, the reason that's there is to offer some voltage difference, of course, because if you just put the bias voltage here, it would hold this voltage at DC voltage, depending on who could win, you know, the voltage swing. Now, the reason it's 47K is trying to match the input impedance of this pin with this one, and this has a 47K. It also has a 10K, so this guy technically should be the parallel equivalent of these two, okay? So this guy should be actually that if you want to get the same kind of leakage current in both pins. So they just use 47K, probably just use values that were similar to the other ones, but it might have been better to just use 10K. That would have been closer to the parallel equivalent of those two. Same with C3. So C3 is a filter pin coming in here. It's a small value, but it's still maybe too large, and we'll see on the Bode plot, okay? But it's the same value as this one, because again, we're trying to match the input impedance of this. So that's kind of the idea of the value of these two parts. And the function. The function is noise, high frequency noise. The function of this C11 up here is at some frequency, he's going to be equivalent to this 47K. At that point, the feedback resistor gets smaller and smaller relative to the input resistor, R3. R3, the gain of this guy, you know, regarding the negative input is feedback over input, right? 47K over this, so 4.7. But then we also add 1 because it's a non-inverting signal. We're coming in here. So it really should be 4.7 plus 1, like a gain of 5.7, okay? And so that's kind of gain. So now this output capacitor, same thing as what this input capacitor does.
is that AC couples this signal to this signal. The signal coming in is referenced to ground, so it's swinging around ground. The signal here is swinging around VB. And out here, we want to reference it back to ground again. So we go through a capacitor so that we don't mess up what's going on in the op-amp circuit. And then I added this R load L just to give a reference point back to ground on the output. So there's actually a little bit of current going through this capacitor. So, and I put 20K just thinking like, well, if you're going into the input of the amplifier, maybe you have 20K input impedance. So I just kind of put something there. It'll have a function because it'll have kind of a RC filter function, so there'll be some roll off at some frequency when this guy becomes equal to the 20K at whatever frequency that happens. Okay, then now down below it, I just have the duplicate circuit, and I call this right output, right input, and left output and left input. Okay, and so here's the bias network for both of them. Here's a bias one. This one, I roll over it, you can see it highlight both. Here's the VP. That's the positive voltage coming in. So that's it. That's the circuit. So let's go ahead and run AC analysis, just like this thing says. So come up here. I could come down here and probe AC, so I can just probe around, and I'll do that in a moment. But let's just run the AC analysis. Now, I had to come up and change this window because before I just had, we're gonna plot the log, the dB of V out, but since I made it left and right, I made this left and the phase. So we're gonna plot the gain of the V out. The reason we don't have to do V out divided by Vn is because Vn's 1 volt. So I just made it 1 volt to make that easy. So otherwise we'd go V out divided by Vn. And phase, same thing. Okay, so let's go up here, and here's the range that's going to run it in. This is from my previous circuit, which will be pretty close. Okay, now there we go. Here's the phase down here at the bottom. We're missing kind of the top of it, so let me double click this, and we'll say that here, this is the phase, and that's the Y. The X is fine. We're going out to 20K, so let's just say the Y. Let's go to auto scale Y and apply. Say OK. So there you go. So it starts off with kind of a positive 20-degree shift, comes down to 0, and then drops off, and about 20 degree is out here about 3K, right? 2, 3, maybe 3 or 4K, somewhere out here. What? Maybe, okay, right there, 4.8K. So that's plus 20 to minus 20, but then it continues dropping all the way down here at 20K, and we're below. What phase are we there? If I hover over there, 43, almost 44 degrees minus. Now up here, our dB V out L is off grid too, so it started at 20, went to 70 from the last thing I did. So here, let's double click that. I think it's a preamplifier for a phono deck or something that I was doing. So here, let me do the same thing. We're on V out up here. See, on this tab, the tabs across the top, I'm on scales and formats. There's a bunch of tabs, as you can see. So I'm going to come over here and say auto scale this guy too. Come down here and say apply, and there it goes. Okay, and look at that. So the input, it actually rises a little bit. So there's a little bit of attenuation from that input capacitor at the input, just a little bit. But if I hover there, it's about 15 dB, and then it comes across up to, it's like 15 dB up here, right? And then, so if we're at 12 dB, which is right here, that's a 3 dB cutoff point. That's at 10K. So at 10K, approximately 10K. Maybe if I hover over that, we'll get a little closer to 12K. At 12K, we're at 3 dB roll off. So, I'd prefer that to come out here farther and at 20K to be 3 dB, or even be flat at 20K. I mean, just to be, kind of a perfectionist. That's the way I would like to see it done. But it drops down to about 9, a gain of 9 at 20K. So yeah, so that's what that guy's looking like. And I think on the bench, we're going to see, the result should be very close to this. Anybody that's a member of the channel or Patreon, if you want a copy of the schematic, just let me know and I'll send it to you. Or even if you're a subscriber. If you're a subscriber, I'll send it to you, okay? Just email me. All right, guys, so I also want to do a little tutorial here. I want to show you these windows up here. There's this cascade one you hit, and it cascades the windows, and I believe, that makes it easy so you can just toggle through different windows here. There's a side-to-side one, okay? Now, let's see, put the graph on the left, but I think if I highlight this tab here and I hit that, yeah, it puts it to the left. So if I, now because it's highlighted here, it's active, right? It's an active window. If I go top and bottom, it puts on top. If I make this one the active window, it puts it up there. And then if this interesting looking one, okay, so I'm going to make the schematic active just to show you something, because this one's different. This one always puts the graph up here, I think. I haven't gone into great detail to try to find out if I can swap that, but it would be cool to put the schematic up here. Now you can do it manually by just adjusting the window sizes, because you can come down here to these tabs and switch them this way too, right? So you can grab a window and change the size. But yeah, these automatic windows are pretty cool. Now this one is where, here, just go full size and it'll make that screen full size. And again, you go down the tab, click it to that one. But if I had had the schematic active when I did that, for instance, if I'm top and bottom, if I go schematic active and I go full size, it'll make that full size. Okay, just wanted to point out some of that stuff, just a little bit here and there. Here, let's close this window, hit the little X here. Now what I want to do is come to analysis, and instead of hitting the AC up here, I want to go probe AC. Now that allows me to, here, let's go side by side though. And then I'll scroll the window over here so I can see the schematic. Yeah, the full schematic. Okay, and you know what, we'll scroll up so we can see the top of that just to make, yeah, there we go. All right, so now if I look at the input, its gain is 0 because it's 1 volt and that's gain is 0. So now if I go to the other side of the capacitor, see what the effects of this RC is, and you can see it's a high pass filter. It filters out some of these low frequencies, and at 3 dB point, if I hover, it's right about there. There's other ways I can do it. I can use these bars up here and all that stuff, right? But if I just hover, kind of point and go, yeah, it's right around there. That's right around 30 hertz, 10, 20, 30 hertz. We could adjust the value of one of these parts to change that, right? Okay, now let's go over here. I think we make this to say 10 microfarad, then it would be way out here and come up. So now we come to the output, and we can see how it has it's a low pass, right? Now it's the high frequencies are being filtered out. Okay, so we come up here, it's about 15 dB, and we come to about 12 dB, right around in here, and say, yeah, that's right around the 3 dB point. So then we go to the output of this to see if this RC is going to affect it, and it doesn't. It puts it right on top. So that's because the roll off of this one is a much higher. This one right here is a dominant roll off. So we could change this to say a 200 puff, for instance. Here, let's just do it real fast. Let's change that to say 220, an actual value. And by making it smaller, it should make it better for high frequencies. Let's see what happens. Yeah, see, it pushed it out a bit. So maybe we want to make that 100 puff. Whoops, there we go. And now look, now we're almost flat out to 20K. So that's how you can play around the circuit and you look at your gains and all that. Okay, now I'm going to go and undo those two things. So as long as my window's active, I'll undo things in this one. So undo, undo, and I'm back to 330. I just want to do this just so that we can look at the original circuit and play around with it. So let's close that window. Let's go analysis. Let's do probe transient. Okay, now we should see the actual waveforms in time domain. Okay, so here's time down here, and here we are. So it's 1 volt peak, minus 1 volt peak. Now let's go to the other side of the capacitor. It should strip off the DC voltage, you know, and it should be floating over here, okay? DC voltage is referenced at 0, so it should not be referenced anymore. Let's see what happens. Nope, it's referenced at VB, 7.5 volts. So it's up here at 7.5 volts. Same waveform, just reference on the 7.5 that's injected right here. Okay, so that's forcing this to float at 7.5. Now what we can do is we can come over here at the output, and there we go. We see the gain, and it's in phase and everything with the input. But look at this, we are getting a little clipping top and bottom. So all right, but it is centered around that 7.5 volts. So inside these capacitors, inside C7, 5, and 1, we're getting you know, it's floating off of the grounds. Okay. All right. So now if we come over here to this side, we're referenced back to ground. So we should see that go back to ground as reference point. So let's do that, and there it is. So now it's referenced around ground. Okay. And it's still flat topped. So if I hover over that 5.5, I can measure it different ways, but I'm just doing this quick. So we got about 11 volts peak to peak, right? And we have 15 volts here. So that means that, you know, this op amp's not a rail to rail op amp. And so we would want to put higher voltage or get a different op amp if we wanted to put 1 volt peak in there and not have it flat top. All right. So, hey guys, just want to show you that. See if you thought that was interesting, and let me know, okay? And by the way, this window, if we want to zoom in on the whole circuit, we could click on auto scale. There's a whole circuit, or we could, you know, magnifying glass, zoom in, zoom out. There's a whole circuit again. So, just want to show you those kind of things too. Little tutorial along the way, right? Alright guys, let me know what you think. Let's jump back in the video. Alright guys, so we have the Omicron Lab running, the Bode Analyzer Suite, and this thing, you know, it does such a great job at Bode. You can do all your setup here on the left, and you know, you can plot the number of points, set the receiver gains. Down here in the left corner, it shows you the signal coming from the output going into the device unit under test, in this case our little op amp board or preamp, and channel 1 is monitoring that voltage, channel 2 is monitoring the output voltage. Takes the gain, and we see it here in the red, the y-axis here on the left in decibels magnitude, so around 15 dB, and then we roll off and look at that, around 10 kilohertz. If we look down 3 dB at 12, we come over here and it's right at about 10K. It looks like that's what they kind of designed it for, right? Now, we have these things up here, like these traces. I could set one of these at 100 Hertz so we could get a reading there. So I'll do that, 100 Hertz. And I'll set the other one at 10K just for fun. 10K. Alright, so it shows you the delta in this bottom row, but it shows 15 dB, and down below 10K is 12.2 dB. So that's one of the ways you can measure these things pretty easily. And when I set this up, I can look at this Bode 100 setup here. There's a lot of controls here. You kind of find a lot of these on the left border over here, but it kind of shows you the picture. You know, probe 1 and the output are connected together going into the input of the DUT, device under test. the output, probe 2, and if you want to attenuate those signals like I have up here, you can do all that kind of stuff. But yeah, it's just a really cool tool. I really like this thing. It's really easy to use. Over on the right, trace 1 is magnitude, the red, and there's our setup for that. And trace 2 is our phase, and here's our plus minus 90 degree setup for that. And that's the axis here on the right. And along the bottom you see 10 hertz to 100 kilohertz. So yeah, there you go, guys. It's a pretty easy setup, pretty nice to use. I really enjoy using this tool. It's always so quick and easy to use, and that just makes it fun. All right, let's get back to the video. All right, guys, what do you think? Now, one of the cool things about it is that it takes a single supply voltage, right? 12 volts. That was pretty neat. Just 12 volts. The way they've got it configured, you don't need a plus minus voltage. So that makes it simple to use. There you go. And, it takes just a moment to settle in, but seems like a pretty nice board. It's especially nice as a test bed to test out different op amps before you put them in your circuit. So I think it's great for just doing that alone. At $4.99, it's hard to go wrong with this little guy. And it comes with the chip and all the parts, as well as the PCB that you can use. If you want to swap out the caps for real high quality caps to make your test bed like as great as you can, you sure can do that. So it's easy to modify the board. Modifying that capacitor will give us a wider bandwidth, or even the input resistor. But I think we'll change that capacitor out. So yeah, easy fix. So what do you guys think? Let me know. Hey, I want to give 2 thumbs up to all my Patreons. Really appreciate you guys. You become a patron for as little as $1 a month. Links down below. I want to give 2 big thumbs up to Omicron Lab for this device here. I've had this around the lab a little bit. You guys might have seen it in other videos, but man, that is one special piece of equipment. It does a lot of things, but the Bode plots is one of the simple things it does, but it does it very nicely. So I really like it. I just upgraded the software for free, of course, because they send out free upgrades. 2 big thumbs up to my members of the channel, especially my team member. Thank you very much. I appreciate that. Yeah, that's pretty cool. I got a team member. I've got, I think, 5 members now. So, oh, and I want to give 2 thumbs up to those guys who've been hitting that super thank you button. God, the last video I think I did, I've got a couple super thanks out of that. So that was awesome. Northox, thanks so much, man. He's been hitting that hard. So buy me a beer. That's pretty sweet. All right, guys. Hey, let me know if you want to buy me a beer. Hit that super thank you button. If you want to support the channel for free, hit that thumbs up button down there, okay? That helps me. So appreciate it, guys. And let me know in the comments what you'd like to see. I think in the future, I'm going to figure out a test. Let me know what you guys think of an op amp shootout. Like, I'll try different op amps in this board and do different tests on it, okay? And so I've got to set up the board. Let me know what you guys think. Give me your comments down below what you think, how I should do that. But for now, it's pretty cool. You got the schematic for this. And yeah, so we're ready to go forward, right? Thanks for watching, guys, and we'll see you next time.